Hi, Precal. My daughter was sick this weekend, so I am home with her today. But I do want to go ahead and do 3.4 notes with you guys. The key for the 3.3 homework is on Blackboard. There are multiple ways to do the solutions to those problems. So just because I have it written one way on the key doesn't necessarily mean that yours is incorrect. So long as you're using those trig identities, reciprocal identities, factoring, common denominators, all that good stuff that we talked about last class. We will have a quiz over 3.3. So you'll want to study your homework, you'll want to study the problems and the notes, and that quiz will be on Wednesday. Okay. So do look at that. I will pick up the homework assignment, that 3.3 homework, on Wednesday. So go ahead and check yours with the key that's on Blackboard. If you want to turn it into the box today, that's fine. If not, on Wednesday, I will take those when we have our quiz. For today, we're going to work at 3.4. So I'm going to go ahead and switch on my video so we can look at the notes together. Okay, so we're looking at 3.4, solving trig equations. So when we're solving a trig equation, we want to try to isolate the trig function on one side of the equation, just like we would in an algebraic equation. You know, we want to move all of our x's to one side and all of our constants to the other. Same thing here. We're going to want to move all our trig to one side, all our constants to the other. We do want to write our answers in exact values rather than decimal approximations. So that does mean using our radians in terms of pi normally. Okay. We're going to take note of whether a problem gives an interval in which to find all the solutions. So we'll only look at solutions that are appropriate for that interval, or if we're just going to find general solutions. In general solutions, we may have some stuff with n's, where n is an integer. So that we can write it for all kinds of different stuff. So there are infinitely many solutions to these trig problems. That's why sometimes they're limited with an interval, or we're going to determine general solutions so that we don't end up listing out all of them. If our trig functions are sine, cosine, cosecant, or secant, we're going to add plus 2n pi to give a general solution. For tangent and cotangent, we're going to add plus n pi. I sometimes write pi n. It's just however you guys want to do that. Okay. So for this first example, I'm going to subtract radical 2 on both sides and add sine on both sides. That way, these are going to cancel. I'll get 2 sine x on this side. These will cancel, and I'll get that it is equal to negative radical 2. Okay. To get sine by itself, I'll go ahead and divide by 2. Okay. And we're looking for, if we're looking for a general solution, we're going to have to add some stuff to this. We know that one period of sine goes from 0 to 2 pi. And we want to find where is sine x equal to negative radical 2 over 2. And if we look at our unit circle, we will see that that is at 5 pi over 4 and 7 pi over 4. Okay. So when we're writing our general solutions, we're going to put the x is equal to 5 pi over 4 plus 2 pi n, or 2n pi, okay? And the x is equal to 7 pi over 4 plus 2 pi n, okay? And that is our solution, okay? With example 3, we have 3 tan squared minus 1 equals 0. We're going to add 1 to both sides. Sorry, I just had some trick-or-treaters at my door. So we added 1 to both sides. So we have 3 tangent squared x equals 1. And then I can divide by 3. Okay. I still have tangent squared, and I'd really like tangent. So I'm going to take the square root on both sides. And of course, I really would like that rationalized. Okay. One period of tangent is from 0 to pi. Okay, and if we need to refresh periods, that was in chapter 2 or unit 2. We know that tangent x is equal to plus or minus radical 3 over 3 at pi over 6 and 5 pi over 6 on our 1 period of tangent. So our general solutions are going to be pi over 6 plus pi n and 5 pi over 6 plus pi n. Okay. Example 3, I'm going to try to move all my trig to one side. So I'm going to have cotangent of x, cosine squared, minus 2 cotangent equals 0. Okay, so I just moved that that 2 cotangent to the other side. I see here that all of my terms have a cotangent in them, so I'm going to factor out cotangent x. Cosine x, or cosine squared x minus 2. Okay, so I have 2 factors here. Just like in factoring in algebra, we can set each factor equal to 0. And solve. Okay, so I have cotangent x equals 0, and on the unit circle, that is when x is equal to pi halves plus pi n, of course, for our general. And we also have that cosine x is plus or minus radical 2. That is not a solution on the unit circle. Because remember that cosine can only be in -1 to 1. Okay, so our only solution is the general solution that x is equal to pi over 2 plus pi n. Okay. If we have equations that are kind of quadratic looking or a quadratic type where it looks like ax squared plus bx plus c equals 0, we want to go ahead and factor those. If it is not possible to factor, then we will have to use the quadratic formula. And remember that is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay. So in example 4, we want to find all the solutions of this trig equation. We notice it is quadratic because we have a sine squared, then sine, and then our c. And it is in an interval, which means this is not a general solution problem. Okay. So if we don't want to factor with sine, remember that we can use a different variable. So we can do it with y's. Okay. This would factor into 2y plus 1, y minus 1. Okay. And once we factored it, then we probably want to go ahead and plug back in that we let y equal sine x. So we'll have 2 sine y plus 1 times, or sine x, sorry. And then sine x minus 1 equals 0. We'll set both factors equal to 0. And kind of solve. Okay. We know on our unit circle from 0 to 2 pi that sine is equal to negative 1/2 when x is 7 pi over 6 or 11 pi over 6. And sine is equal to 1 when x is pi over 2. Okay, so those are our solutions. Again, we don't have to add 2 pi n or anything like that to it because we're not looking for a general solution. We're looking strictly inside of our interval. Okay. If we go ahead and look at example 5, we'll see again, this looks kind of quadratic, except for I have sine squared and cosine. And I really would like it to be an all one trig equation. Luckily, we know a trig identity that will put sine squared into cosines. And that would be 1 minus cosine squared x. I am going to leave my 2 outside. Okay. I can go ahead and distribute this 2. And then I see I have some like terms I can combine. Okay. I find that it's very hard to factor when a is negative. So I'm going to multiply this entire equation through by a negative. And that way, this is a little easier to factor. Remember, we can factor it with a different variable if we need to. and then plug back in cosine when we're done. We'll set each term equal to 0. And solve. And again, they didn't give us an interval this time, so we are looking for general solutions. Okay, so we actually have 3 general solutions here. We have x is pi over 3 plus 2 pi n. We have x is equal to 5 pi over 3 plus 2 pi n. And we have the x is 0 plus 2 pi n. Or if we wanted just to write that as x is equal to 2 pi n, that would be fine. Okay. For example 6, again, we're in an interval, so we're not general solutions this time. We have cosine x plus 1 is sine x. We know something similar to this is a trig identity that would help. So we're going to start by squaring both sides. Okay. When I square cosine x plus 1, I'm going to get cosine squared x plus 2 cosine x plus 1. Okay, it is a perfect square. So we're going trinomial, so you do have to remember that it's cosine squared times 2 times the middle plus 1. So do FOIL it out, and that is equal to sine squared x. Again, we're doing this because we want to get rid of the sine eventually. And we know that sine squared x is the same thing as saying 1 minus cosine squared. Okay, now I can add these to the other side of the equation. So if I add cosine squared, I'll have 2 cosine squared. And I subtract this 1 over, and those will cancel, sorry. Okay. We can factor out a cosine because I have a cosine in each equation or each term. Actually, I have 2 cosine in each term. So here I'm left with cosine x plus 1. I can set each factor equal to 0. And solve for x. Okay. So here are my 3 solutions that are inside the interval. We do need to check these, which we haven't done on previous problems, and it's because we squared both sides. Okay, so I do want to check that they work. So pi halves, we're going to have cosine of pi halves plus 1 equals sine of pi halves. Cosine of pi halves is 0 plus 1. Sine of pi halves is 1, so this checks out. We'll check 3 pi halves. Okay. Cosine of 3 pi halves is 0 plus 1. Sine of 3 pi halves is -1. This does not check out. So 3 pi halves is not a solution. The last one we need to check is pi. cosine of pi is -1 plus 1. Sine of pi is 0, so this one will check. So our solutions are going to be pi over 2 and pi, but not 3 of pi over 2. So if we square both sides, we do need to check. That is important. As we can see, one of those does not contribute to a solution. Okay. When we're solving equations of trig functions of multiple angles, such as cosine of kx or tangent of kx, we're going to first solve the equation for that kx and then divide our result by k after generalizing. So if I'm looking at example 7, we have 2 cosine 3t minus 1. I'm going to start by moving the 1 to the other side, dividing by 2. Okay, so I have that cosine of 3t is equal to 1/2. I know that cosine of 3t is equal to 1/2 when 3t is equal to pi over 3 or 5 pi over 3. So again, I'm going to my unit circle and I'm looking for where is cosine 1/2. Ignoring the 3t for right now, I'm saying these are my 2 spots, okay? So then I'm going to set these equal to my general 3t equal to my general solutions. Okay, and I still need to divide by 3, and I'm going to divide everything by 3. So I'm going to have that t is equal to pi over 9, because I divided by 3, so my new denominator is 9, plus 2 pi n over 3. I divided this thing by 3 as well. So then the second one will yield 5 pi over 9 plus 2 pi n over 3. And these are going to be my 2 general solutions for this problem. Okay. Same kind of deal in example 8. I'll start by subtracting 3 and solving for tan of x over 2. Then dividing off that 3 in front. Okay, so we have tangent of x over 2 is -1. I am looking for where tangent is -1 in my unit circle. And I know that x over 2 will be that at 3 pi over 4. That's the only place. Okay, plus pi n. This time, instead of dividing, I need to get rid of this. So I'm going to multiply everything by 2. That means that will cancel with that 4 in the denominator. So I'll have 3 pi over 2 plus 2 pi n, because I multiplied that by 2 as well. Okay, last bitty thing, using the inverse functions. Every once in a while, we need to do that. Okay. So this first one, well, this only one, this last example, we have secant squared minus 2 tangent equals 4. Again, we want it in all one function, but we know that secant squared is 1 plus tangent squared. And I'm going to go ahead and move this 4 to the other side so that it is equal to 0, and I'll combine with that 1. Oops. Okay. Then I can factor. And we'll set each factor equal to 0. Oops, -1. These are not things that we can easily find on our unit circle. So we want to use inverse trig functions. So this one's the easier one to start with, this tan x equals -1. We'll say that x is equal to arctan of -1. And if we're looking at that, that would be -pi/4 on our unit circle. Okay, so that one's a little easier to find. This one, tan of x is equal to 3, is defined, but is not exact on our unit circle. So we'll have the x is equal to arctan of 3, but beyond that, you would want to use a calculator. Okay, so our general solutions, we're going to have -pi/4 plus pi n, because it's tangent, and arctan of 3 plus pi n. Or if we went to our calculator, that would be approximately 71.57 plus pi n. Okay. And there's our solution. Homework is going to be on WebAssign 3.4. And then again, you have that quiz next class. And I will see you guys on Wednesday.